In this video, we present SIRA-PCR, sim-to-real adaptation for 3D point cloud registration. Given a source point cloud and a target point cloud in arbitrary poses, the objective of point cloud registration is to attain the rotation and translation that align the source to the target. Recent data-driven deep learning-based methods have attained remarkable success in indoor scenarios. These methods usually extract features using feature descriptors, then find correspondences depending on feature matching, and finally estimate transformation with a traditional or deep robust estimator. For obtaining a reliable feature descriptor, training with high-quality data is needed. To support the training, commonly used datasets can be divided into two categories: object level and indoor scene level. However, the model trained on the synthetic object-level dataset can hardly generalize to real-world indoor scenarios, since the object data has strong shape priors while the geometric structures in indoor scenes are much more complex and diverse. Though directly adopting real captured datasets can produce satisfying performance, collecting a large amount of data is highly time-consuming. Also, obtaining accurate ground truth labels is expensive, since the estimated camera poses are prone to errors, so human annotations are needed. A straightforward avenue is to utilize synthetic data, where both the data collection and annotation are automatic. However, it lacks complicated geometric structures, which are essential for training a robust feature descriptor. Second, the low-level distribution gap between simulated and real data. The feature descriptor is sensitive to this, such as point pattern difference and noise. To address the first problem, we propose flying shapes, which contains two main parts: geometric augmentation and high-quality viewpoint selection. We augment geometric structure diversity by randomly adding and arranging objects from ShapeNet into scenes of 3D front. Specifically, physically based insertion is to simulate the cluttered item combinations placed on furniture in the real world. It randomly arranges objects on the top of the furniture until collision happens. Random insertion is to randomly scale, rotate, and place objects in the empty space of each room. To find a proper viewpoint to obtain an informative point cloud, we utilize the number of materials in the captured view to filter the views lacking geometric structures due to few furniture. Finally, we render and collect the corresponding depth images using the viewpoints selected, and turn them into point clouds. To mitigate the low-level distribution gap, we develop a generative sim-to-real adaptation pipeline, named SIRA. Given a synthetic point cloud, the generator adjusts its point positions but keeps the original shape. Then, the discriminator is adopted to determine the real-fake classification of the low-level point distribution. To make sure the extracted feature contains enough geometric information, we perform the above process on each local patch of the input point cloud independently. In particular, we design an adaptive resample module, ARM, and insert it after different layers of the generator to adaptively adjust point positions in multiple ranges. ARM can modify point positions while keeping the input outline. We construct a local patch using the neighbors for the input points. Then, we compute weights using their corresponding features. Each output point is the weighted sum of all neighbors, resulting in its position within the convex hull of the patch. As the neighborhood is chosen small enough, this process can be regarded as points resampling in patches. Here we show the evaluation results on the indoor 3D match benchmark and the outdoor ETH benchmark. It shows that our model clearly outperforms the previous state-of-the-art method. At last, we provide some qualitative comparison with previous state-of-the-art methods. The codes and datasets are available on GitHub. Please check it out. Thank you.